half the squared error, you minimize the error. Right? The reason people put half is kind of almost historic. One good thing that it has is if your error is squared, then you take a derivative, you'll get 2 of the error. Right? X squared derivative is 2 of x. You get a lot of happiness if you cancel. You see what I'm saying? When things aren't going well, you're stuck in the exam. Oh my God, I can cancel this, I can cancel this. You see what I'm saying? So then your 2 gets cancelled and somehow you get some happiness. Okay, that's about the only reason. Of course, there are other ways of saying things, like for example, half sometimes comes up for, in all sorts of ways. In physics, for example, half mv squared is your, kinetic energy. But in general, as far as learning is concerned, you could have just minimized this. It doesn't make any difference at all. But people just think in terms of, mean squared error is half of the squared error. Now notice that I'm only looking at the Sj minus, the value that currently the thetas are saying minus the value it should have. From the point of view of actual temporal difference learning, the actual value that should be there would be what this alpha times reward plus beta times the value of the next state. Remember, that's the target. Okay, and you want to nudge it towards that. So that's how you get that other next value. But for now, assume that that value is known, this value is known, and you're just trying to change the thetas. So the question is, how much are you supposed to change the thetas? The whole discussion we have done is you can change the thetas in the direction that was opposite to the gradient. If you can compute the gradient with respect to each of the thetas, okay, each theta now is a variable because you're trying to set them. And they're all continuous variables. So you're going to essentially try to set theta I to be theta I minus alpha times the partial derivative of the error term with respect to theta I. Okay? So now a little bit of differentiation. Now, in fact, it turns out that this is the value function, right? And the error is in terms of the value functions. It's the square of the value function minus the correct value. Okay? But then what you're trying to do is differentiate with respect to theta. The theta is inside of this. That's where you use the chain rule. Right? So what do? You say the derivative of Ej with respect to theta I is derivative of Ej with respect to the V theta. Just imagine V theta itself is a variable. And then derivative of V theta with respect to theta I. You could have any number of these chains in general, but here it just had to be 2-level chain differentiation. Okay? Yes? So the question then is what happens here? So if you look at, I'm trying to compute this. So this is alpha times dou Ej by dou theta I, where this part, the Ej, if you remember, is half of V theta minus V Sj squared. So if you just differentiate this part as if V theta is itself a variable, right? Then what do you get? You get 2 times V theta minus V. Okay, so that's basically what I had here. 2 times V theta minus V, and then the half that was sitting there gets cancelled with the 2. So you just have V theta minus V. That's your Ej with respect to the derivative of Ej with respect to V theta. And now I have to differentiate V theta with respect to the weight itself. Now, of course, this depends on how value is represented in terms of the features. For us, it's just a linear function, right? So remember that my value function is this. Now I'm going to differentiate this function, this linear function, with respect to theta I. So let's say I'm differentiating with respect to theta 2. The guy in the red shirt in the back. Hello? What's the answer?
2.
You come to the class not to just write the code. Understand?
Yeah.
Okay? Please pay attention. Otherwise, there's no difference between being here and sleeping and sitting at home and sleeping. Anyway, so what's the answer for somebody who's actually paying attention? F2. You see what I'm saying? Right? Because if theta 2 is the variable, then theta 1 doesn't change with respect to theta 2. So that becomes 0. And this is theta 0. That will become 0. Theta 1 doesn't change. That will become 0. 0 times anything is 0. This theta 2 is changing with respect to theta 2 exactly. So d theta by theta is 1. Okay? So then you get the F2 here and everything else is 0. So what I got was the differential is just the feature value for the jth dimension. Okay, so I did all my calculation and then essentially I got theta I should be shifted towards alpha times Vsj minus V dash theta Sj times Fi, feature Fi for that state. Because I'm essentially differentiating with respect to theta I. Right? Questions? Anybody? This is just calculus coming back to bite you. Right? Yes, please, go ahead.
Why are we studying only about convex and not
No, I didn't say anything about convex. Right now, this is my function. I was just telling earlier that if your error function, unbeknownst to you, happens to be a convex function, then when you reach the minimum, that would be the only minimum in the world. And so you would have gotten the global minimum. But that's a different point from here. Here I'm just going through the machinations. So I will change the theta I, every theta I, a little bit in proportional to its gradient times alpha, which is the learning rate. Now notice that this change is done for each of the thetas. So the best way to think about this is you have a weight vector, theta 0 to theta k. The entire vector is being pushed in the correct direction by taking the gradient vector times alpha. So you get a new weight vector. And you keep doing this in essence, and at some point of time you stop and you hope for that. Basically, as you come to, one of the good things is, as you come to the part of the error function that actually is the minimum, what will happen to the gradient? It will become 0. So the weights will stop changing once you get to the minimum. At that point, say the weights are not changing, I stop. In fact, most people don't do that. They just keep going for a while and then stop. And then say, like Columbus, I must have reached minimum. Okay? So this, by the way, is essentially, your, this is what we do. Yeah, this is essentially your gradient descent based value function approximation. And I did it with respect to linear error. Okay, so if you think in terms of how this gets plugged in, this is your temporal difference algorithm. At some point of time, you have to update the V value previously. Now you update the theta values. Instead of updating the value of the cell, you update the theta values. When you update the theta values, you don't change just that cell value, you change everybody else's value to a little bit. Just like when I updated the relative weights for assignments to get somebody's grade fall below threshold, everybody's grade changed. We call that a feature, because in some sense it's generalized across all the states with the similar features. So in particular, what we are doing essentially is this Vs, the actual value that you are trying to push the V theta towards, is given by your temporal difference formula. You see what I'm saying? Okay, so that is Vs is R of S plus beta times V theta of S dash. Beta times value of the neighbor you found, S dash. Now it turns out that the value of your neighbor is also in terms of this formula. So one somewhat deep technical point that I won't go into is actually you are changing the thetas while using the theta values. Okay, so if you read more serious reinforcement learning textbooks, they point out that what we are doing here is not exactly gradient descent, it's called semi-gradient descent. But as far as this class is concerned, we just call it gradient descent. And that'll be fine. Okay, so now the next thing is, I did that for temporal difference. Could I have done this for Q learning? Yes, I could have done it for Q learning too. The only thing is, essentially, the real value for the Q learning comes from the max part, minus whatever is the Q value currently for the S and A. And that's being minimized, that error is being minimized. And in general, if you go through the error, the gradient calculation, you notice that the gradient calculation didn't really depend upon the form of VSJ. It's just V of Sj minus this. So instead of this being a temporal difference based value, it could be a Q learning based value. You see what I'm saying? In general, all the gradient difference updates would be proportional to the difference between the real and what you want it to be. Okay? Okay, so did people get this? That in essentially this thing is sitting here because this is the value that you want it to be. This is the value it currently is. And in trying to push it in the right direction so that the thetas will change correctly, you are essentially changing thetas, not the values, to the original theta values times alpha times this expression, which just happens to be the gradient. It just happens to be the gradient under two assumptions. Assumption one is that you have a linear weighted function or features. You are defining value as Wi times Fi. The second assumption is that the error is being defined as a square of the difference. Those are the two things that you used in the derivation, right? So this is the error, this was squared because of it was V minus V dash squared, V minus V hat squared, and so that became 2 times V minus V hat. Had this been defined in a different formula, as the error is defined in a different formula, which you will be seeing in a minute. In fact, if you suddenly defined error to be V minus V hat power 4, you could do that. Okay, and then when you are minimizing that, then of course this part will now have a 3 term, 3 times V minus V hat power 3. Do you see that? And similarly, this part became just F2 for you, just Fi for you, because the way you combined the features into value is a linear combination of features. Do you see what I'm saying? Okay, if you did something else, then you have to differentiate that function. Now, here is an interesting thing. If I'm actually, instead of doing this, if I considered not only these, but I also considered plus theta 1 to power f1 square plus theta 1 to theta 2 to power f2 square, etc. You see what I'm saying? I'm now considering not just the feature values, but the squares of the feature values in defining the value function. Right? The question is, if you take a differential of this, will it have the same nice property that we had before? How many people think it won't have the same nice property as before? How many think it will have the same nice property as before? What are you differentiating with? What? Theta. Did I square theta? Did I square theta anywhere? No. This is, by the way, I'm sorry. If you didn't hear me saying it, it looks like this is squared, but I was just saying, okay, let me call it theta 1, 2 here. Theta 2, 2. Let's just wait. Yeah, I know it's a bad example. I take it back. Okay. So theta 1, 2 f1 square, theta 2, 2 f2 square, etc. Now the question is, now I'm essentially taking a linear sum, not just of the features, but linear sum of the features, square of the features, cubes of the features, etc., etc. Will this change the differential? No. Wherever it used to be f2, it will now be f2 square. Wherever it used to be, do you see what I'm saying? This is actually a game that we will play later on. This is essentially called sort of kernel trick. You can take the values of the features and start squaring them, and you will start getting more interesting ways of differentiating, doing classification with no extra cost in terms of doing the actual differentiation. Had I, however, started doing theta square, then the differential will change. You get this? Okay, I'm sorry for the wrong example, but I was trying to say theta 1, 2, and that's not, but you probably didn't hear it, and you just said theta 1 square. That looked like that. Okay. So keep that in mind, that there is a large number, any linear function of features, even if you are taking squares and cubes of the features, will still be a linear function. But in general, the reason, when you do this, by the way, here is an interesting thing. If you started with 4 features, okay, it was a 4-dimensional optimization problem. Now if I started having theta square, theta 1 square, theta 2 square, etc., etc., now it's become 16 features. Because you'll have to also consider theta 1, not f1, f2, f1 square, f2 square, etc., f1, f2, f1, f3, etc. This is essentially increasing the dimensionality of the data in terms of features. In general, in machine learning, people always talk about reducing the dimensionality of the data to make life simpler. But if you increase the dimensionality, you can make life simpler in a different way. You can essentially wind up using linear feature functions, which wind up having very nice properties such as, for example, perceptrons can differentiate pluses and minuses. Yes, go ahead.
One question, Professor. That's why I said, like, why convex?
What?
Why not concave? Like.
No, it just, in this particular case, this happens to be that. I'm just taking this part. So for any specific error function I start with, it has its own properties.
Okay.
And it turns out that for a single case, so let me just get through that. For what we did till now essentially gets us to, two things. I'll actually skip all this right now. You can think of this. This is what you've been dying to see. It looks like a nice neural network, right? So you can all take a deep breath. Now we are in happy life. So it turns out that if you feel like thinking of whatever we just did, what we did is called linear regression. You say linear regression in bold letters on your resume and wait for people to call you. They don't call you for interviews. If on the other hand you say, I did deep learning with one neuron, one layer, linear threshold function, these guys say, my God, this guy knows something. And remember, we saw the Nature paper, which did exactly that. Basically, they did this 10 or whatever, 13,000 parameter function, and somebody else said, you could have done it with one neuron, man. And that one neuron looks like that. Okay, yes?
Where does the threshold before you call it learning versus deep learning?
The normal definition is the number of layers, and that's the thing. Okay. So in this particular case, so you can think of this as a perceptron. Imagine this is a thing where you are introducing the features here. F1, this is F0, F1, F2, etc., Fk. You're introducing the variables, the weights here, theta 0, theta 1, theta k. The semantics are that when I do this, then I do theta I, fi. And normally I also have the semantics that then I apply a function g to this and output it. For now, assume g is identity function. If you assume g is identity function, this is a single perceptron where you are feeding the feature values here and it is predicting the value outside. And you are training these thetas, you are training these weights such that the values become closer to the correct values. This is linear regression. Okay? Now, and then so of course, then you start saying that this sort of looks like a neuron, okay? And then you can start talking about neural networks, but let's go further one more. If you actually start caring about value function in reinforcement learning, that's a real number. If on the other hand, you're using the learning techniques to predict the policy, what action should I do at every state? Imagine this is a discrete action space MDP, which is the ones that we have seen. Remember the up, down, left, right. There, you will then be required to predict the correct action, which is a categorical attribute, which is a categorical value. There's left, there's up, there's down, there's left, there's right. Or north, south, east, west. Those are the only actions. There is no 0.3 times north plus 0.7 times south kind of an action. These are the four actions that you have. Okay? If you are learning there, then you are going from a domain which, you're taking a feature vector of the state and you are trying to say what should it be in terms of the four actions. Which action should it be? It's a slightly different problem from regression problem. It's called classification problem. Because the outcome now is a discrete set of categorical values. You see what I'm saying? Regression and classification are very closely intertwined. The difference is in the case of classification, you are putting out discrete values. In the case of regression, you're putting out continuous set of values. Okay? Now, it turns out that I already told you that if I have G equal to identity, then this is linear regression. I can start having G to be any arbitrary functions, and typically the kind of functions we will look at are what are called the gating functions, threshold functions. Okay? The simplest threshold functions are the step functions, which basically say if this value that is coming out here is equal to or greater than some number, then it is +1, otherwise it's 0. Step functions are bad. Step functions are great to understand gating behavior. They're bad because what is our hammer? What is our hammer? Gradient descent. Everything has to be learned with gradient descent. That means you have to do differentiation. Have you ever tried to differentiate a step function? You cannot differentiate a step function because it's discontinuous. It's the same reason you don't use the absolute value. In the case of absolute value, it's actually continuous, but it's not differentiable because the slopes are different. Here, it's not even continuous. The value just jumps from one place to other at the same value. So in fact, it's not even a function because at 0, it's both +1 and -1. Okay? This is what I'm saying? Okay, so then if you do this, then essentially notice that if I start having a threshold, you can almost see how a linear regression with a thresholding, a gating function, can start becoming a classifier. Because if it is above a certain value, it will say yes, otherwise it will say no, as a categorical attribution. Okay, the obvious thresholds we talked about are these gates, the step functions that are not good, but it turns out that you can have other continuous functions which look like step functions but are differentiable. One of the most useful ones that everybody talks about is 1 by 1 plus e power minus x. That's called a logistic function, a sigmoid function. And the sigmoid function is clearly, if you think in terms of how it will look as a function, right? If x equal to minus infinity, this will be 1 by 1 plus e power minus times minus infinity, which is 1 by 1 plus e power infinity, which is 1 by a huge big number, which is 0. So on this side it will be 0. On the plus infinity side it will be 1. Because x will be infinity and minus e power minus infinity will be 0. So 1 by 1 will be 1. At x equal to 0, what happens to this function? At x equal to 0, it will be 0.5. Because at x equal to 0, it will be 1 by 1 plus e power 0. So 1 by 1 plus 2. 1 plus 1, which is 1 by 2, which is 0.5. So this function will be sort of going from minus infinity to plus infinity, while plus infinity side will be +1, minus infinity side will be 0, it will be crossing here. And in fact, the way it crosses would be nicely like that. So for all practical purposes, it's the kind of function that we are dreaming about. It's the step function. It looks like a step function. And yet it is differentiable. And furthermore, its differential has a beautiful property. If you think of g of x equal to 1 by 1 plus e power minus x, then g dash of x will be shown as g of x times 1 minus g of x. In fact, the little review that I sent you about multivariable calculus had this as one of the examples. Okay? Now see, as we are going, you can see how what is doable with math and what you want to do are getting intertwined. Really what you wanted to do is step function. But what can be differentiated is sigmoid, so we'll go with it. Okay? Now interestingly, if I put g equal to sigmoid, that is 1 by 1 plus e power minus x, and do the same perceptron, I come like this close to one of the greatest ideas in machine learning. It's called logistic regression. It's called logistic regression. It is, the name is made to make you go crazy. Because you think regression means it is actually computing a continuous value. But logistic regression is actually used for classification. But the way you think of output of logistic regression is as the probability. So which is actually a continuous quantity. So we came from linear regression with one switch, by just changing the G, we started now having, logistic regression. I said almost. The one other difference is if you are doing this, in fact, if you're doing this, let me just show you that. If you're doing the perceptron with logistic regression function, 1 by 1 plus e power minus x as the thresholding function, you can do your weight update rule. Let me first walk you through this and then tell you this is almost logistic regression but with a difference. Okay, so let's go through this weight update rule. Here, essentially, unlike the last time around, I am considering, so I have like a perceptron like this. I have a whole bunch of feature values, and I want to sort of say yes or no outside. Let's say there are only two actions, action 1 or action 2 is what I'm trying to learn. And this is all called supervised learning. That means for some number of training examples, you know what the answer is. In the online temporal difference learning, you did have that, right? Because the temporal difference was telling you what the right answer is. Okay, and that's what you pushed yourself towards. So here I assume that I've been given a training data which are described in terms of features and the correct label, 1 or 0. And I will start with some variables. So now I'll just give up on thetas. I'll start thinking in terms of wi's. I'll start having weights on these links. Weights on these links. Okay? And then I will wind up essentially, if I'm using those weights as the current input, I can compute what comes out using the thresholding function. And you compare that to what should be coming out, which is the true value for that particular example. And you want to take the difference, square it. Because remember, we're still thinking in terms of squared error. Unlike the RL example where we were doing online learning, here I don't have to do online. I can do offline learning. Which means I've been given like 10,000 examples. So I pass all the 10,000 examples through this, figure out what each of them, what is the error. And so the error for each of the examples will be the true value for that example minus what the output is from the perceptron. I square it and I sum this over all the examples. This is the cumulative error over the training set. Right? And I will then essentially try to minimize that error. And if you go through the same sort of process that we did last time, the T is the true value, so there is no structure to it. That's just the correct value. That's what you've been told. What you come as the O, however, is the weighted sum of the inputs for the J example